Light. It moves through the universe at 299,792 kilometers per second. It is not merely fast, it is the fastest thing that can ever be. In every direction, across every galaxy, light marks the ultimate boundary between motion and stillness, between cause and effect. Nothing with mass can ever match it. No signal or whisper of information can outrun it. It is the heartbeat of reality itself. For centuries, light was thought to be an ethereal wave, an unseen vibration moving through some invisible substance that filled the cosmos. Scientists called it the luminiferous ether, a medium that carried radiance from the sun to Earth. But when experiment after experiment failed to detect that medium, a young patent clerk in Bern would later remove it entirely from existence. That man was Albert Einstein. His insight would do more than explain light. It would rewrite time, space, and gravity themselves. Imagine you are standing beneath the clear sky. The sun's glow touches your face. The light that warms you left that distant sphere of fire just over 8 minutes ago. What you see is not the present sun, but its past. Every sunrise is a memory still racing toward you. And yet, for most of human history, people believed gravity acted instantly. They imagined that if the sun suddenly disappeared, Earth would be torn from its orbit in the same moment. It felt intuitive. Gravity was the invisible hand that held everything in place. Surely it must act without delay. But that would mean gravity travels faster than light. It would mean information moves instantaneously across space. It would mean cause and effect have no separation at all. That idea cannot survive the laws of relativity. If the sun were to vanish right now, Earth would continue to orbit the empty point in space for 8 minutes more. For those 8 minutes, the sunlight would still bathe the oceans. The blue sky would still shine, and our planet would keep following its curved path around where the sun used to be. Only when the last photons of light reached us, 8 minutes later, would the shadow of loss arrive, and with it, the change in gravity. Einstein realized that gravity is not an invisible force that leaps across emptiness. It is a message written in the geometry of space-time itself. When a mass moves or disappears, the shape of space-time changes, and that change ripples outward at the speed of light. Those ripples are what we call gravitational waves. They do not stretch through a medium. They are the medium. They are space-time, flexing and relaxing, like the surface of a vast cosmic ocean. This truth reframes everything. The universe does not allow instant action. It allows only light speed reaction. The speed of light is the speed of causality, the speed at which reality updates itself. To understand what that means, imagine the sun again. It bends space-time around it, sculpting a gravitational well that guides Earth's orbit. When the sun moves slightly, that curve in space-time shifts too. But the new shape of that curve cannot reach Earth until light from the sun's new position arrives. The planet does not orbit a static point, but the dynamic curvature continually refreshed at light speed. Einstein's equations predicted this with mathematical precision, but it would take a century to prove it. Until the 21st century, gravity's true velocity remained untested. Astronomers could not watch space-time ripple, they could only infer. But in the year 2017, two neutron stars collided 130 million light-years away, sending out both light and gravitational waves. The detectors at LIGO and Virgo felt those waves, and telescopes across Earth caught the flash. The arrival times matched within a fraction of a second. That single cosmic event told us that gravity travels at precisely the same speed as light. The illusion of instant gravity had finally been broken. The cosmos has one ultimate limit. Light sets that limit. And gravity, bound by light, tells us that even the fabric of space-time must obey it. Every star that burns, every galaxy that spins, every motion we witness is choreographed by this law. No signal of cause can outpace the radiance of consequence. Yet this revelation births another question, deeper and stranger. If gravity and light share the same speed, what happens when mass approaches that sacred boundary? What happens to the very geometry of space-time when matter moves so fast that time itself slows to a crawl? That is where our journey leads next. The speed of light is not simply a number. It is the rhythm by which the universe keeps time. Every motion, every vibration, every gravitational tug obeys it. If there were some hidden corridor faster than light, the order of cause and effect would unravel. You could see an event before it happened. You could watch a star explode and then watch it form. The cosmos forbids that reversal. It protects the arrow of time by capping the velocity of information. When Einstein wrote his special theory of relativity, he did more than explain why nothing can move faster than light. He showed that the speed of light is the same for all observers, no matter how they move. That constancy means space and time are not separate. They are woven together so that what one observer calls distance, another may call duration. The faster you travel, the slower your time runs. That slowdown is not an illusion. It is a reshaping of reality. Picture a spacecraft moving near the speed of light. Inside, a clock ticks slower than on Earth. To the traveler, everything feels normal. The heart beats, the seconds pass. But to the universe outside, the traveler's time stretches thin. This is time dilation, one of the most beautiful consequences of relativity. The faster you go, the more the universe bends its laws to prevent you from reaching light speed. And this limit is absolute. To accelerate of a single grain of dust to the speed of light would require infinite energy. As it gains speed, its energy, and thus its effective mass, increases. It becomes heavier, not because new atoms appear, but because its energy curves space-time more strongly. To reach the speed of light, the energy required grows without bound. Infinity cannot be reached by finite means. This is why nothing with mass can ever travel as fast as light. The closer you get, the slower your time flows, and the harder you must push. The energy you pour in goes into stretching time itself. Eventually, all the effort in the universe would not be enough to gain that final fraction of speed. Light is not just fast, it is freedom from mass. And yet, light also experiences time in a way no human can imagine. To a photon, the moment of its birth and the moment of its death are one and the same. It does not age. It does not wait. From its own perspective, the entire journey across the cosmos happens in an instant. A ray of sunlight striking your eye left the sun 8 minutes ago. But for that photon, there was no travel, no passage, no waiting. It existed at emission and absorption as one seamless event. That timelessness is what binds light and gravity. Both are carriers of information, moving at the same speed. Both define the structure of space-time. Light tells us what happens. Gravity tells us where it happens. Without light, there is no seeing. Without gravity, there is no stage for seeing to occur. As stars move, they disturb space-time, sending tiny ripples that stretch and squeeze everything in their path. These ripples, gravitational waves, carry news of motion across the universe. But unlike sound in air, these waves do not need a medium. They are the medium. They are space-time itself in motion. It is strange to think that emptiness can ripple. Yet this is what the detectors at LIGO have recorded. A stretching of reality so faint that it moves the mirrors by less than the width of a proton. From such faint trembling, we learn that the cosmos is alive with motion. Every black hole merger, every spinning neutron star, every cataclysm hums across the cosmic web. This is why the illusion of instantaneous gravity was so persistent. The scale of these effects is vast, but the speed of light is enormous. Over the distance between the Sun and Earth, light takes only 8 minutes. For the outer planets, a few hours. For nearby stars, a few years. To us, those times feel immediate. Only when we look across galaxies do we see the delay stretch into millennia. When we gaze at Andromeda, we see light that left that galaxy more than 2 million years ago. Any changes in its gravitational pull would reach us just as slowly. The universe speaks, but its messages take ages to arrive. And yet, this limit preserves reality itself. If gravity could act instantly, causality would collapse. An action here could affect a place beyond our future light cone. The order of events would lose meaning. Relativity saves the logic of existence by ensuring that every effect follows its cause through the slow, steady march of light. Einstein's vision replaced the universe's old mechanical clockwork with something far more elegant. Space and time are not empty backdrops, but participants. They flex, stretch, and fold under the influence of energy and momentum. Matter tells space-time how to curve, and space-time tells matter how to move. This exchange, this conversation, travels at the speed of light. Imagine the cosmos as a grand symphony, and light as its tempo. Gravity, the melody. Matter, the instruments. Each star, planet, and atom plays its part, guided by that unbreakable beat. When one note changes, the rhythm adjusts across the entire orchestra, but never faster than light can carry the news. The question then is, what happens when we approach that tempo's ultimate limit? What happens when something with gravity itself begins to move so fast that it challenges the very curvature that defines it? Can space-time still hold its form? Does gravity itself transform at that boundary? To find the answer, we must leave behind the comfort of slow motion and step into Einstein's deeper vision, where gravity is not a force, but a geometry. Light draws a line across reality, a perfect threshold between what can be and what cannot. Everything slower than light experiences the flow of time. Everything that would try to be faster ceases to exist as matter at all. The boundary is not a wall that stops motion, it is a rule that defines existence. At that boundary, something remarkable happens. The universe changes language. For ordinary objects, motion and gravity are separate ideas. A planet moves in the gravity of a star. A comet falls inward, curving through space. But Einstein realized that this separation was only an illusion born of slowness. To him, there was no force pulling the comet toward the sun. There was only space-time, curved by the sun's mass, guiding the comet along its path. In that vision, gravity is not an action at a distance. It is geometry. This idea grows naturally from the limit set by light. Because nothing can transmit influence faster than light, the only way for gravity to exist at all is for it to be part of the same structure that light travels through. Space and time are not containers holding events. They are the events, shaped by energy and motion. The straight lines of Newton's universe bend into the curved geodesics of Einstein's. When you stand on Earth, you feel your weight pressing down. It feels like a pull toward the ground, but in truth, you are being pushed upward by the solid floor. Left alone in orbit, you would not feel weight at all. You would be moving freely along the curved path that space-time dictates around the planet. The sensation of gravity is the sensation of resisting that curve. The speed of light, the ultimate limit, ensures that these curves can only change at a finite rate. When Earth moves, its gravitational field adjusts, but those adjustments radiate outward no faster than light itself. The same is true of every object in the cosmos. When one star dies, its gravitational signature fades away only after its final photons and gravitational waves reach the rest of the universe. It is a quiet and beautiful synchronization. Every event is chained to its echoes by that single number. It ties light, gravity, and time together in one harmonious constraint. As our understanding deepened, scientists began to realize how profound this connection is. The equations of general relativity describe how energy and momentum warp space-time, and in turn, how that warped space-time directs motion. Those equations are exact and unforgiving. They allow for no instant jumps, no shortcuts, no breaches of causality. They declare that space-time itself can ripple, but those ripples, like light, move only as fast as the cosmic limit allows. To test this, We built machines of impossible sensitivity, long tunnels stretching kilometers in length, filled with vacuum, polished mirrors suspended in silence. They wait for space-time to shiver. When two black holes merge, their violent dance sends waves across the universe, compressing and expanding space as they pass. The detectors feel that tremor as a slight change in the distance between mirrors, smaller than the width of a single atomic nucleus. In that faint motion, we read the story of distant titans colliding. We hear the universe speak in gravity's own language, and in that whisper, we confirm once more that the message travels at the same speed as light. From the smallest atom to the largest cluster of galaxies, this law holds. The geometry of space-time cannot turn or twist faster than light can trace it. Light is not only the fastest traveler, it is the guardian of order. It keeps the cosmos consistent, but in the stillness of thought, a question persists. What would happen if something could reach that speed? If an object with mass could somehow move at the same pace as its own gravitational field? Would it vanish into pure energy? Would space-time tear? The equations of relativity answer with silence. They forbid the experiment. To reach that speed would require infinite energy, and infinity cannot exist within a finite universe. And yet, there is one thing that does travel at that speed: light itself. It has no rest mass, yet it carries energy and momentum. It curves space-time, even if only faintly. In that delicate bending lies the next step in our exploration. Light does not merely move through space-time, it shapes it. It defines the geometry it travels along. Around massive objects, its path bends, tracing the curvature that gravity creates. And in turn, because light carries energy, it contributes to that curvature. The universe is a dialogue between light and gravity, each shaping and responding to the other. Our journey now turns to that conversation. How can something weightless create gravity? How can light, the messenger of the cosmos, also be one of its architects? The answer lies deeper within Einstein's geometry, where energy and curvature are two sides of the same truth. The shift from Newton's gravity to Einstein's curved space-time was not merely a new theory, it was a change in how the universe itself was understood. Under Newton, gravity was a force that reached across emptiness, pulling masses together instantly, no matter how far apart they were. It was a convenient picture, intuitive and comforting, but it rested on an invisible thread stretching faster than light. Einstein saw that this could not be. He imagined what it would mean if light always moved at the same speed, for every observer, no matter how they traveled. From that single idea came the collapse of absolute time and absolute space. What replaced them was space-time, a single four-dimensional fabric that could stretch, twist, and curve. In that new world, gravity was not a pull. It was the bending of the fabric itself. Imagine a vast sheet stretched tight. Place a heavy sphere on it, and the sheet dips. Roll a smaller ball nearby, and it curves toward the dip, not because the larger ball pulls it, but because the surface itself guides its motion. That is what the sun does to space-time, and that is why Earth moves in its orbit. There is no force reaching out across the void, only geometry. Einstein's equations captured this idea in a form both simple and infinite. The stress-energy tensor describes the content of energy and momentum in every point of space. The curvature tensor describes how space-time bends in response. Together they form a relationship. Matter tells space-time how to curve, and curved space-time tells matter how to move. Every planet, every star, every black hole is a sculptor, reshaping the fabric of reality around it. For small motions, Newton's laws are still accurate, just as a flat map can describe a small patch of Earth's curved surface. But when mass is enormous, or motion is fast, the true curvature cannot be ignored. The bending becomes deep enough that light itself follows the curve. Around the sun, starlight passing close to its edge bends by a tiny but measurable angle. During a solar eclipse in 1919, astronomers observed this deflection for the first time. Starlight shifted, just as Einstein predicted, proving that space near the sun is curved. The geometry was real. From that moment, gravity ceased to be a mysterious force. It became the shape of space-time itself. Planets orbit not because they are pulled, but because they are following the straightest possible paths in a curved geometry. To resist gravity is to resist that geometry, and to fall is to surrender to it. This new vision also revealed something subtle. If the shape of space-time determines motion, then any change in that shape must travel as a wave, just as ripples spread when you disturb water. But space-time's ripples do not move faster than light. They move exactly at that speed, carrying information about changing mass and motion across the cosmos. These are gravitational waves, the universe's quiet messengers of motion. To Einstein, this connection between light and gravity was inevitable. If light is the fastest any signal can travel, then gravity too must obey that limit. Otherwise, geometry itself would change faster than its own constraint. That would break causality, unraveling the sequence of cause and effect that gives the universe coherence. The beauty of Einstein's idea is its unity. Space, time, light, and gravity are no longer separate. They are all part of a single structure, bound by the same rhythm. When a star moves, the curvature of space-time changes. That change radiates outward, and every planet, every photon, every atom adjusts in response. The delay is tiny across small distances, but on cosmic scales, it defines the tempo of the universe. Yet this understanding also leads to new questions. If mass can bend space-time, then what happens when motion itself approaches light speed? Can space-time curve infinitely? Can the geometry that defines gravity survive such extremes? To answer, we must look deeper into how energy and motion feed the fabric of space-time. Because in Einstein's universe, energy and mass are the same. And energy, like mass, curves space-time. When Einstein united space and time into one continuous fabric, he also united mass and energy into one continuous concept. The equation that every student of physics learns, energy equals mass times the square of the speed of light, is more than a formula. It is a statement about reality. It says that matter and energy are not two things, but two faces of the same entity. The sun shines because it turns a tiny portion of its mass into energy, flooding the cosmos with light. That light, carrying energy, in turn curves space-time, however faintly. This merging of concepts was a revolution disguised as simplicity. In Newton's world, mass was a measure of how much matter an object contained, and energy was what made it move. But in Einstein's world, the two were interchangeable. A body at rest possesses energy simply by existing. That rest energy, multiplied by the speed of light squared, defines how much it bends space-time around it. This bending is what we feel as gravity. Imagine Earth not as a planet surrounded by emptiness, but as a region of space-time curved into a smooth valley. Everything that moves near it, from satellites to starlight, follows paths shaped by that valley. These paths, the geodesics, are the straightest possible lines in curved space-time. When a comet plunges toward the sun, it is not being pulled. It is sliding down a curve. When it swings around and returns to the darkness, it is climbing back up that curve. In this geometry, there is no distinction between motion and gravity. To fall freely is to move naturally along space-time's shape. To stand still, as we do on Earth's surface, is to push upward against that natural path. That pressure, the effort to resist the curve, is what we call weight. Every step you take is a small act of defiance against space-time's geometry. When Einstein tested his theory against reality, it did not just work. It explained mysteries that had puzzled astronomers for decades.
The orbit of Mercury had a tiny irregularity, a precession that Newton's laws could not explain. Einstein's equations predicted it precisely. This success convinced even the skeptics that space-time curvature was real, that the geometry of the universe is the true origin of gravity. As we map this geometry, we see that it changes whenever energy moves. A spinning star, a collapsing supernova, a merging pair of black holes, all of them twist space-time differently as they evolve. The equations of general relativity predict that these changes travel outward, not as an instantaneous rearrangement, but as waves. These waves are faint distortions that carry energy across the cosmos. When they pass through Earth, they stretch and compress space itself, ever so slightly. In 2015, the Laser Interferometer Gravitational Wave Observatory detected such a ripple for the first time. Two black holes had collided over 1 billion light-years away, and the tremor from their dance reached us after traveling for more than 1 billion years. It moved the mirrors in the detector by a fraction of a proton's width. Yet from that small motion, we could hear the sound of space-time ringing. That sound was not carried through a medium. It was the medium. The universe itself had vibrated. The importance of this discovery cannot be overstated. It confirmed that gravity's changes move at exactly the speed of light, no faster and no slower. The waves arrived when the theory said they would, proving that space-time's communication is bounded by the same law that governs photons. In that unity, the cosmos preserves its order. These gravitational waves reveal another truth. Space and time are not rigid. They are elastic, dynamic, alive with motion. Every star that explodes, every planet that shifts, every orbit that decays, sends out ripples of curvature that fade into the endless background. Though they are almost undetectable, they carry the history of the universe within them. What we call gravity is not a static pull. It is a constant reshaping, a ceaseless update of space-time's geometry as energy moves. The planets do not orbit a fixed map. They trace ever-changing routes through a landscape that is always adjusting, always propagating its own story at the speed of light. To live in such a universe is to live in a web of information. Every particle, every beam of light, every quantum of energy is both messenger and message, influencing and being influenced by the curvature around it. This is why gravity cannot be instantaneous. The story of the cosmos unfolds through signals that take time to arrive, so that
past and future remain distinct, and cause still precedes effect. And yet there is something profoundly elegant in this delay. It gives the universe its tempo. It ensures that the dance of galaxies and stars follows a rhythm rather than chaos. It turns geometry into music. As our detectors improve, we are beginning to listen to this cosmic music more deeply. Each wave we detect is a note in space-time's song. Each tells of a collision, a death, or a birth of celestial bodies. And every note, no matter how distant, moves at the same immutable speed. But this realization leads us to the edge of a new mystery. If gravity and light are bound together by the same limit, what happens when we push that limit? What happens when motion itself begins to approach the speed of light, when energy and curvature become inseparable? To explore that frontier, we must look not at the geometry of slow stars, but at the boundaries of speed itself. There, the familiar shapes of space-time begin to twist into forms that challenge comprehension. Einstein's equations describe a universe that is never still. Every shift of energy, every trembling of mass, every flicker of light contributes to the bending of space-time. It is a vast interplay of motion and form, where the geometry of the cosmos updates itself moment by moment. The speed of light marks how quickly those updates can travel. Beyond that, there is no faster way for information to move. Think of space-time as a fluid sea. Every planet and star rests upon it, pressing down with their energy, creating hollows and currents. When one of them stirs, the disturbance ripples outward. The larger the event, the deeper the waves. And though these waves spread through a dimensionless void, They are as real as the tides of an ocean. They carry momentum, they can do work, and they can merge or cancel as they meet. When two black holes spiral toward one another, their orbit sends out waves of curvature, carrying away energy. Those waves are not emitted by matter itself, but by space-time responding to the motion of mass. Each orbit tightens as energy leaves, the holes circling faster, until at last they collide and become one. The final burst of gravitational radiation races outward across millions of light years, telling the story of that union. When those waves reach our instruments, we can reconstruct what happened from the pattern of space-time's vibration. This vision changes how we think of gravity. It is not a static field, frozen around a body. It is alive, adjusting continuously as objects move. The equations of general relativity allow us to predict exactly how these adjustments propagate. They do so as waves moving at the same speed as light. No part of space-time can feel the change until the wavefront reaches it. In this way, the universe maintains a strict and elegant order. At first glance, it may seem paradoxical that something as heavy and immense as gravity can be so obedient to the same rule that governs the feather-like photon. Yet it is precisely this obedience that unites the cosmos. Light and gravity, though they seem opposites, one carrying no mass, the other defining all mass, are bound by a single limit. That limit is not an arbitrary cap on speed. It is the structure of reality itself. To an observer, this means that the shape of space-time at any point is a record of what has already happened, not of what is happening now. We live always in the past of distant stars. The geometry that holds our planet in orbit is based on where the sun was 8 minutes ago. On cosmic scales, this delay becomes immense. The geometry of our local universe reflects the positions of galaxies as they were millions of years in the past. The shape of space-time is, in a very real sense, a fossil record written in curvature. Understanding this turns the study of gravity into a study of time. The universe is not a snapshot. It is a movie still playing, each frame taking years or millennia to reach us. When we observe gravitational waves, we are hearing the echoes of events long finished, their memory carried across the void by space-time itself. This revelation carries philosophical weight. The cosmos is not connected by instant threads, but by finite, measurable signals. There is no true simultaneity across vast distances. There is only the grand unfolding of influence, spreading outward at light speed, weaving a consistent reality that prevents paradox. The price of order is delay, the reward is causality. It also means that every event, no matter how violent, is contained. Nothing can send a shock that breaks the universal limit. Even when black holes collide, the most extreme event we can imagine, the ripples they create obey the same law. Space and time flex, but they never tear faster than light allows. In this way, Einstein gave the universe both its freedom and its restraint. He replaced an instantaneous force with a living geometry, a fabric that bends but does not break, and through that geometry, he tied every movement of matter to the rhythm of light. The more we test his theory, the stronger it stands. Satellite experiments confirm how time slows in stronger gravity and how light bends around massive bodies. The Event Horizon Telescope has imaged the shadow of a black hole exactly where the equations said it should be. Each observation reinforces the idea that gravity is not a force but a shape. To grasp this is to see the universe not as a stage where matter moves, but as a dance where the stage itself joins in. The curvature of space-time is both backdrop and participant, choreographer and performer. Everything that exists is part of that motion. And yet, as we look deeper, one question grows larger. If gravity propagates at the speed of light, what happens when we reach that speed? What happens to space-time's geometry when energy itself moves at its own limit? The mathematics begins to twist. The familiar curves flatten and sharpen into waves of pure distortion. To explore that realm is to chase the frontier between energy and geometry, between motion and the fabric that contains it. That is where we must go next, to understand the true speed of gravity and what it means for the structure of reality. For centuries, gravity was believed to be instant. Newton's equations worked so perfectly for predicting the motion of planets that few thought to question how that invisible pull traveled across the void. The sun tugged on Earth, Earth tugged on the moon, and the dance of the heavens followed precise rhythms. Yet, hidden beneath that precision was a silent assumption that the pull of gravity reached across space without delay. It was an idea that seemed logical. After all, the distances in the solar system are vast, and the orbits appear smooth. If gravity were slow, wouldn't planets drift out of place before the signal reached them? But Einstein saw that instant gravity was impossible. The notion violated the cosmic speed limit, the same rule that governed light itself. Information cannot move faster than the universal constant. Gravity, as a messenger of geometry, must obey it too. Still, belief in instantaneous gravity lingered. For generations, no one could measure gravity's speed directly. The effect of delay was too small, too subtle to observe across the scale of planets. For a long time, we could only rely on theory. But theories demand proof, and nature eventually provided it. In the year 2017, the universe offered a test. 130 million light-years away, two neutron stars spiraled toward each other. These stars were corpses of suns, their matter crushed so tightly that a teaspoon of it would weigh billions of tons. As they circled closer and closer, they sent out gravitational waves, ripples in space-time that carried away their orbital energy. Their collision produced a cataclysmic explosion, releasing a flash of light, gamma rays, and an immense burst of gravitational radiation. On Earth, detectors called LIGO and Virgo were waiting. They had been built to measure distortions smaller than an atomic nucleus, prepared to feel space-time itself tremble. When the waves arrived, the mirrors in those detectors moved ever so slightly, stretched and squeezed by the passing ripple. 2 seconds later, telescopes caught the burst of light from the same event. The difference in arrival time was almost nothing, no more than a heartbeat. The gravitational waves and the photons had traveled side by side for 130 million years, and they reached Earth together, their speeds matching to within 1 part in 10 to the power of 15. For the first time, we had measured the speed of gravity directly. It was exactly the same as the speed of light. This was not coincidence, it was confirmation. Einstein's prediction, written a century earlier in the Mathematics of General Relativity, was now proven by the cosmos itself. Space-time's ripples and light's waves move through the universe at the same pace. There is no shortcut, no hidden channel faster than light. Gravity is geometry, and geometry travels no faster than the boundary of causality. The realization reshapes how we understand the stability of the universe. If gravity were even slightly faster or slower than light, orbits would distort, galaxies would twist apart, and causality would fail. The perfect synchrony of light and gravity keeps the cosmic structure intact. It also reveals something profound about motion. The bending of space-time caused by a moving mass does not act instantly across the universe. The curvature follows the movement, adjusting with the delay imposed by light speed. A planet does not orbit the present position of its star, but the position corrected by that finite delay. The geometry surrounding it is a living record of where the star was, not where it is now. The entire universe lives in such delayed coordination, each region responding to the past of every other. If we could see space-time as it truly is, we would witness a constant streaming of influence, like ripples overlapping on the surface of an infinite pond. Every motion, every change, sends new waves outward. The pattern is beautiful and intricate, a cosmic tapestry woven from time itself. The experiment of 2017 showed that these ripples are not metaphor. They are measurable, physical, and real. They carry energy,
lose intensity with distance, and obey the same constraints that govern light. In their passage, they can make a ruler lengthen or shorten, though by less than a fraction of a proton's width. They stretch the universe itself, but so gently that only the most sensitive instruments can feel it. Each detection tells a story. The first, from two black holes merging, was a whisper of violence. The second, from the neutron-star collision, was a symphony of matter and light. Each new signal teaches us more about the fabric of space-time, how it responds to mass, energy, and motion. And always, the waves move at the one universal limit, neither surpassing nor lagging behind light. To think of gravity this way is to realize that nothing in the cosmos acts alone. Every object, from a grain of dust to the largest black hole, sends its presence outward at light speed, forever shaping the geometry around it. The field of gravity that holds us to Earth is not a static structure, but a continuing conversation between matter and space-time. The universe, then, is a web of communication bound by time. Every star, planet, and photon participates in this exchange. When one moves, the others eventually respond, each at its own delay. The limit imposed by light speed gives the cosmos coherence, ensuring that no message arrives before its cause. And yet, in that harmony, there is a question that still presses against the boundaries of understanding. What happens to gravity when motion itself approaches the speed of light? If an object could move so fast that its own gravitational influence barely kept up, how would space-time behave? Would the curve flatten into a wave? Would gravity turn into pure radiation? To explore that, we must look not at the speed of gravity as we measure it, but at the nature of mass, energy, and motion itself, at how gravity responds when matter races toward the ultimate limit of reality. As matter rushes toward the limit set by light, the geometry that holds it begins to change. When motion is slow, gravity curves space-time smoothly, creating orbits, tides, and familiar arcs. But as velocity climbs toward light speed, those gentle curves flatten, compressing forward like waves before the bow of a ship. The faster a mass moves, the more its gravitational influence concentrates in the direction of its motion. Einstein's equations describe this precisely. The field around a fast-moving body is no longer spherical. It becomes distorted, a flattened ellipsoid sweeping through space-time. To an observer ahead of it, the gravitational pull seems sharper and more intense, while to one behind it, the field stretches thin. This effect is not due to any change in the substance of matter, but to the way space-time itself measures distance and time for something moving so quickly. Imagine watching a massive particle accelerate to a fraction of light speed. The geometry surrounding it begins to lean forward, its influence piling up into a kind of gravitational bow wave. If that particle could reach the ultimate speed, the distortion would collapse into a shock front, a single sheet of curvature racing outward at light speed. This idea is captured mathematically by what physicists call the Eichelberg-Sexel ultraboost, a solution to Einstein's equations describing an object moving at the speed of light. In that extreme, gravity becomes a pulse, not a field. Such pulses are not fiction. They are close relatives of the gravitational waves we now detect. Every time two massive objects move or collide, they send out bursts of curvature that travel exactly at light speed. These are space-time's shockwaves, carrying the story of violent motion across the universe. They have no medium, no carrier. They are the fabric itself shaking off the energy of change. The 2017 neutron-star merger showed that these pulses arrive in step with light, proving that space-time communicates its own motion at that same immutable rate. The precision of that match, 1 part in 10 to the power of 15, tells us that gravity does not hide a deeper, faster mechanism. The curvature of space-time and the flash of light are two expressions of the same event. When we model these phenomena, we see that space-time behaves like a fluid that cannot be compressed beyond a certain point. push energy into it faster, and it simply reshapes itself to preserve the limit. That reshaping is what we perceive as time dilation and length contraction. At near-light speeds, time slows, distances shrink, and the geometry adjusts so that no matter how much energy is added, the boundary of light speed remains unreachable for anything with mass. In the moments after the Big Bang, when the universe was young and dense, matter and light moved together through a sea of extreme curvature. In that era, gravity waves and light waves were indistinguishable. Space-time vibrated as a single entity. Only as the cosmos expanded and cooled did light separate from matter, carrying with it the same speed that defines gravity's reach. The two have been linked ever since. To think of this is to glimpse the architecture of reality. Gravity does not chase light. It is light's geometry. Every photon that crosses the universe travels along the very curves that gravity shapes, and those curves change only as fast as the photon can move. The limit is not a boundary imposed from outside. It is the structure of space-time itself, the rate at which existence can communicate its own form. If we could ride on a gravitational wave, we would experience a stillness unlike any other. The wave moves at light speed, so for it, time does not pass. The crest and the trough exist together, an eternal ripple frozen in motion. To us, crossing that wave would feel like moving through a heartbeat of the cosmos, a brief, silent pulse in which space expands and contracts by a billionth of a fraction before returning to calm. In this way, the speed of gravity is not merely a number. It is the expression of reality's most fundamental symmetry. Light and gravity travel together because they are born from the same fabric. The universe can bend, stretch, and vibrate, but it cannot communicate those vibrations faster than the rhythm of its own nature. This understanding marks the end of the old notion of force and the beginning of geometry as truth. The sun does not pull on Earth. The moon does not tug on the tides. Each body simply shapes space-time, and those shapes move and interact at the one constant velocity that defines causality. The universe updates itself, pulse by pulse, at light speed. From this realization, a deeper question emerges. If nothing can travel faster than light, and if gravity itself is bound by that same rule, what happens when space-time is curved so intensely that even light cannot escape? What becomes of geometry when it folds back upon itself? The answer lies in the next frontier, the place where gravity and light meet at their absolute limits. As mass and motion grow extreme, the fabric of space-time begins to twist in on itself. The ordinary rules that keep light free and gravity gentle start to blur. Where gravity is weak, space-time curves only slightly, creating the soft depressions that shape orbits and tides. But as mass increases or motion nears light speed, those depressions deepen until they threaten to collapse entirely. What begins as geometry becomes destiny. Imagine a star 10 times heavier than the sun. Its light struggles to escape, its atoms crushed beneath their own attraction. The greater the mass, the stronger the curvature, until eventually no known force can resist it. The star's core caves inward, shrinking beyond comprehension, and space-time folds so tightly around it that escape becomes impossible. This is the birth of a black hole, a region where gravity bends light back upon itself. In this environment, the speed of gravity and the speed of light are still equal, but the paths they follow have become trapped. Near the boundary, called the event horizon, all routes that light might take lead inward. There is no outward direction left to travel. Gravity does not outpace light here. Rather, the geometry of space-time has turned every possible path toward its center. It is not that gravity moves faster. It is that space itself now points only one way. For an outside observer, time near the horizon seems to slow. A beam of light climbing out takes longer and longer to reach freedom, until it appears to freeze. A falling object, seen from afar, never quite crosses the edge. its image lingers, stretched and redshifted, fading slowly into darkness. But for the object itself, the crossing happens in an instant. The flow of time depends on where you stand in the geometry, and near a black hole, geometry and time are inseparable. Even here, the law of light speed holds firm. No signal, not even gravity, can emerge from beyond the horizon. The information about what lies inside is sealed away, hidden by the very structure of space-time. The surface of the event horizon is not a physical wall. It is a boundary in time. To cross it is to move forward in a direction that always leads deeper. The equality between light and gravity remains intact. The difference is that the geometry has become so steep that every light-speed path is curved inward. Gravity does not travel faster than light. It bends the stage upon which light moves until all roads lead down. This idea is not an abstraction. It defines how the universe's most massive objects behave. Black holes merge, producing gravitational waves that ripple outward at light speed, while their event horizons grow to enclose the new geometry. The speed of gravity, unchanged, continues to shape and propagate the story of these collisions. Even in their silence, the holes speak through those waves, sending the memory of their union across billions of light years. To understand what happens at that edge, we look at something called the photon sphere. It is a narrow band surrounding a black hole where light can orbit endlessly. Here, the balance between gravity and motion is exact. A photon moving sideways at this distance neither escapes nor falls inward. It circles the black hole in a closed path. Gravity and light are locked in a dance at the same speed, each chasing the other around the curve of space-time. In this place, time almost stops. To an outside observer, the photon's orbit appears eternal, but a slight nudge inward sends it spiraling to its doom, while a nudge outward lets it escape. The photon sphere is the frontier where the speed of light meets the full curvature of gravity and survives, barely. Beyond it lies the event horizon, where not even that balance can hold. Inside, all paths curve inward through time. The geometry is absolute. Gravity does not need to move faster than light because it has already rewritten the map of movement itself. The very meaning of direction has changed. This union of limits, where light speed and space-time curvature converge, is not a breakdown of physics, but its perfection. It shows that the cosmic speed limit is not a wall that stops motion, but a sculptor that defines existence. The universe can bend as deeply as it must, but it cannot send any message, any influence, faster than light. Even at the edge of a black hole, this law remains sacred. From these depths, we learn something profound. The limit set by light does not constrain the universe's creativity, it shapes it. The delay between gravity and light is not a flaw, but a rhythm, keeping the cosmos coherent. When black holes form, merge, or spin, they show us that even at nature's most extreme, the same speed governs all things. As we move forward, we will explore what this means for space-time itself. When gravity becomes so strong that it traps light, how does the geometry behave? What happens when light's own energy curves the very fabric it moves through? In answering these, we will discover that light too can have gravity, that even the fastest thing in the universe cannot escape the geometry it creates. In Einstein's universe, everything that has energy also has gravity. The two are inseparable, bound by the equation energy equals mass times the square of the speed of light. This simple expression, compact and elegant, hides a truth as vast as the cosmos itself. It tells us that energy and mass are not opposites but twins, different forms of the same essence. A star burns by trading mass for energy. A particle moving at near light speed gains energy and, with it, gravitational influence. In this way, motion itself becomes a kind of weight. Imagine a single grain of dust floating in deep space. At rest, it curves space-time so faintly that its presence is almost nothing, but begin to accelerate it.
As its speed rises, so does its energy. And because energy and mass are equivalent, that motion increases its gravitational pull. The faster it moves, the stronger its effect on the geometry around it. If we could somehow accelerate it endlessly, its energy would climb toward infinity. Its gravity would become infinite as well. Space-time itself would collapse under the weight of that motion. This is why nothing with mass can ever reach the speed of light. The barrier is not mechanical, it is geometric. As speed increases, time slows for the traveler, and the universe reshapes itself to preserve the limit. To reach the speed of light would require infinite energy, and infinity has no place within a finite cosmos. The closer one gets, the more nature resists, stretching time and compressing distance until the pursuit of light speed becomes impossible. Energy, then, is the architect of curvature. Wherever energy resides, space-time bends. The more energy concentrated in a region, the sharper the bend. This relationship defines everything from the orbit of planets to the collapse of stars. It also explains why light, though massless, can still shape the universe. Light carries energy and momentum, and thus it contributes to the curvature of space-time, however slightly. To picture this, imagine a beam of sunlight traveling through the darkness between worlds. Each photon in that beam carries momentum. As it moves, it interacts with the geometry around it, bending gently near massive bodies. But the photons themselves also warp space-time, leaving the faintest imprint of their energy upon the fabric they cross. The effect is so small that only in the densest fields, where billions upon billions of photons converge, does light's gravity become noticeable. Yet it is there, written in the equations of relativity, as precisely as the pull of a planet. When energy increases, its gravitational field strengthens. This is why motion changes gravity. A fast-moving object behaves as if it were heavier than it is at rest. Physicists call this relativistic mass, but it is not new matter appearing. It is energy taking on the geometry of mass. The field surrounding such an object becomes directional, flattened and compressed along its path. To an observer, it looks as if the object's gravity is leaning forward, dragged by its motion. This effect is subtle at ordinary speeds, but grows immense as the velocity approaches that of light. The equations show that as kinetic energy rises, so does the curvature it generates. Yet that increase never breaches the cosmic limit. The geometry simply adjusts, protecting the speed of light as an absolute boundary. This protection is not enforced by any force, but by the structure of space-time itself. The universe maintains its consistency by ensuring that nothing with rest mass can move as quickly as its own influence. Energy's equivalence to mass also explains the life cycle of stars. When nuclear fusion occurs, small amounts of mass vanish, replaced by enormous amounts of energy. That released energy, streaming outward as light and heat, carries away the mass's gravitational contribution. Over billions of years, this slow conversion shapes the star's evolution, gradually altering its balance between pressure and gravity. Eventually, when the fuel runs out, the loss of energy allows gravity to dominate and the star collapses inward. Even in that collapse, energy remains the sculptor. The falling matter compresses, heating until its internal energy resists further contraction. But if the mass is great enough, not even energy's pressure can stop the fall. The geometry deepens until a singularity forms, a place where the energy density becomes infinite and the equations of relativity reach their edge. The same relationship governs motion on smaller scales. In particle accelerators, protons are driven to speeds approaching that of light. Their effective mass increases, and their collisions release energies great enough to recreate conditions from the early universe. At such speeds, gravity's role is still small compared to other forces. But the principle is the same. Motion is energy, and energy bends space-time. In the grand scale of the cosmos, this connection between energy, mass, and gravity is what allows structure to exist. Galaxies form where energy cools and slows, letting curvature gather matter into stars.
Black holes form where energy concentrates beyond escape. Even the expansion of the universe is an expression of energy-shaping geometry, driven by a form of energy we call dark energy, an unseen influence that stretches space itself. Everywhere we look, energy defines the map of reality. The stars, the light they emit, and the gravity that binds them are all different languages describing the same story. As motion and energy intertwine, another question arises. If light carries energy and can curve space-time, does that mean light has its own gravity? Can something that moves at the universe's limit also shape the geometry it rides upon? To answer that, we must step beyond the domain of matter and explore light itself, not as a traveler through space-time, but as a creator of curvature. As we turn our attention to light itself, we meet the purest expression of energy in motion. A photon is a bundle of energy with no rest mass. It carries momentum, it exerts pressure, and it always moves at the cosmic speed limit. Light does not need to be pushed, it simply exists at that ultimate rate. It cannot slow, it cannot rest, and it cannot accelerate. It is both messenger and manifestation of the law that binds the universe together. If light carries energy, then by Einstein's equation, it must also possess gravity. But how can something that has no rest mass create curvature? The answer lies in the way general relativity defines energy. Gravity is not a property of matter alone. It is a response to the presence of energy and momentum. Wherever there is energy, space-time bends. The equations do not distinguish between mass and pure radiation. The stress-energy tensor, the heart of Einstein's formulation, includes all forms of energy, mass, motion, and light alike. This means that photons, though weightless, curve space-time. The effect is faint beyond imagining, yet it is real. In ordinary light, the curvature is far too small to notice. But if light could be concentrated enough, if trillions upon trillions of photons were compressed into a narrow beam, their combined energy could shape the geometry around them. The universe rarely arranges such densities naturally, but the mathematics allows it. In principle, a sphere made entirely of trapped light could collapse under its own gravity, forming what theorists call a geon, a self-contained ball of radiation bound by the curvature it creates. Even before such extremes, the gravitational behavior of light can be seen in the way beams interact with massive bodies. When a ray of starlight passes near the sun, its path bends slightly. The photons are not pulled by a force, but guided by the geometry the sun creates. The same curvature that keeps planets in orbit also redirects light. This bending, first observed during the solar eclipse of 1919, confirmed Einstein's prediction and changed forever how we perceive the cosmos. We now know that light's path is not straight through space, but through space-time. Its apparent straightness is the natural path within a curved geometry. The photon is always following the straightest possible line, even when that line loops and bends. To us, the curve appears as deflection. To the photon, it is still the shortest route allowed by space-time's shape. The gravitational influence of light itself has been observed indirectly in the phenomenon known as gravitational lensing. When a massive galaxy cluster lies between us and a distant source, its gravity bends light into arcs and rings. The cluster acts like a cosmic lens, magnifying and distorting the background. Yet the light also contributes minutely to the total curvature. The energy within those photons adds to the overall geometry. In the great equation of the cosmos, nothing is ever truly weightless. This realization invites a thought experiment. Suppose a beam of light circles endlessly within a mirrored sphere. The photons would move at the speed of light, reflecting again and again, adding their energy to the same region. That energy would curve space-time inward, pulling the mirrors closer together. If the energy were intense enough, the curvature could trap the light entirely, creating a self-gravitating sphere of radiation. Such objects, though theoretical, reveal the universality of gravity. Wherever energy gathers, curvature follows. In the vastness of space, we see hints of this principle in the most extreme astrophysical events. In the early universe, when light and matter were intertwined, the radiation density was so high that it shaped the expansion of space-time itself. Photons and neutrinos provided pressure that resisted collapse, while their collective energy bent the cosmos outward. Even today, the cosmic microwave background carries the imprint of that early balance between light and gravity, a fossil glow marking the first dance of energy and geometry. It is humbling to realize that the same light we see from stars participates in sculpting the universe. Each beam, faint as it may be, contributes to the total curvature of space-time. The glow of a galaxy, the pulse of a quasar, even the quiet starlight crossing interstellar dust, all of it plays a role in the grand architecture of the cosmos. Yet, for all its subtlety, light's gravity reveals something profound about the symmetry of nature. The fastest thing in existence, the thing that sets the speed limit for all others, still obeys the same law it defines. It cannot escape its own rule. The photon, racing at the ultimate speed, still curves the space-time it traverses and still follows that curvature faithfully. In its motion, we see the universe respecting itself. At human scales, this effect is invisible. At cosmic scales, it sculpts entire galaxies. Streams of radiation from quasars can influence the motion of nearby gas and dust. The faint pressure of sunlight can alter the orbits of asteroids over millions of years. Though light's gravity is weak, its energy is relentless. Time and distance magnify its influence until it becomes one of the quiet architects of structure. The relationship between energy, motion, and curvature is now complete. Every form of energy bends space-time. Every movement shapes geometry. Even light, the swiftest traveler, is a participant in that endless dialogue. But what happens when light meets gravity at its strongest? When photons orbit a black hole, chasing one another at the edge of the abyss, the two limits of nature, speed and curvature, collide. It is there, in the narrow band where light can circle forever, that we see gravity and energy locked in perfect equilibrium. That realm, the photon sphere, is where light bends itself. When light nears a region of intense gravity, it reveals the most intricate dialogue between energy and space-time. Every photon, though massless, feels the curvature it helps create. When it passes near a massive body, its path bends. When it moves through a gravitational well, its frequency changes. To climb outward costs energy. To fall inward gives it energy. The color of light itself, its wavelength and rhythm, shifts with the geometry it travels through. The universe writes its gravity into light as redshift and blueshift, signatures of curvature etched into the spectrum of stars. Nowhere is this conversation between light and gravity more dramatic than near a black hole. At a certain distance from the center, called the photon sphere, light can orbit endlessly. The speed of the photon is the same as always, 299,792 kilometers per second. But here that speed matches perfectly with the curvature of space-time. The photon does not spiral inward or escape outward. It loops, chasing itself around the black hole in a perfect circle. In this narrow ring, gravity and motion balance at the edge of possibility. Every photon in that orbit is suspended between freedom and imprisonment. To an outside observer, it appears as if light is frozen in motion, neither advancing nor retreating, forever sliding along the bent geometry of space-time. The photon sphere is not merely a feature of black holes. It is the physical embodiment of light and gravity reaching equilibrium. If you could hover just above that sphere, the sight would defy imagination. Looking ahead, you would see your own back. Light emitted behind you would curve around the black hole and return to your eyes. The night sky would fold. Upon itself, every star's image warped and multiplied in endless rings. This place is neither fully space nor time as we understand them. It is a boundary, a mirror made of geometry. At this distance, the speed of gravity and the speed of light are indistinguishable. Both travel along the same curved paths, both trapped in the same relentless orbit. Space-time is no longer merely the stage for motion, it is motion. The photon's journey defines the curve, and the curve defines the journey. Light and gravity cease to be separate concepts. They become the same phenomenon observed from different directions. But there is no stability in perfection. A photon circling in this ring is balanced on the edge of chaos. A slight nudge outward, and it escapes to infinity. A slight nudge inward, and it plunges past the event horizon, never to return. The photon sphere marks the last stand of light against the pull of gravity, the outer wall of space-time's absolute curvature. What lies within that boundary is not merely darkness, but transformation. Inside the event horizon, every possible path bends inward. Space and time trade roles. Motion through space becomes motion through time toward the singularity. The photon cannot escape, not because it slows, but because all possible routes now lead inward. The geometry itself demands it. Gravity does not overtake light. It redirects the definition of movement until outward no longer exists. In this way, the equality between light and gravity remains unbroken even at the threshold of the abyss. The speed of light continues to set the limit, but the shape of space-time has changed so drastically that the concept of escape has lost meaning. To fall beyond the horizon is to cross into a region where the direction we call forward in time is also downward in space. Every ray of light, every line of causality, ends at the singularity where curvature becomes infinite. From the outside, however, the black hole is silent, almost serene. It communicates only through gravity and the faint waves that ripple from its mergers or accretion. Those waves travel outward at light speed, carrying with them the imprint of the geometry that created them. They tell us that even at the most extreme, space-time obeys its own law. Information moves at the cosmic speed limit, never faster, never slower. This understanding reframes what we mean by gravity itself. It is not a pull downward, but a distortion of what forward in time means. Near Earth, that distortion is gentle. We feel it as weight. Near a black hole, it becomes so steep that forward in time points toward the center. Every motion, every photon, every pulse of energy must follow it. The photon sphere thus stands as a monument to this law. It is the final orbit where energy and geometry coexist as equals. Beyond it, space-time curves so deeply that the rules of distance and time dissolve into one another. The black hole does not break the cosmic speed limit. It bends the very framework that defines it. In that bending lies the essence of relativity. The speed of light is constant for all observers, but what counts as distance and what counts as time depends on the geometry surrounding them. When gravity is strong enough, it can stretch or shrink those measurements until even light cannot find a path outward. Yet through it all, the speed remains the same. This balance between unchanging speed and mutable geometry is what makes the universe stable. Light defines how fast reality updates. Gravity defines how it bends while doing so. The interplay of the two governs everything from the paths of planets to the birth of stars and the quiet hum of cosmic expansion. To see light orbiting a black hole is to glimpse the ultimate unity of motion and curvature. It is to witness energy held captive by the very geometry it helped create. The photon sphere is not a failure of physics, but its triumph, a place where the cosmos reveals that its limits are not boundaries but harmonies. And yet, questions remain. If light can bend itself in the grip of gravity, could a universe made purely of radiation sustain its own geometry? Could energy alone, without matter, shape space-time into something stable? To answer, we must look deeper into what happens when light and gravity are not merely partners, but indistinguishable parts of the same vibration, when space-time itself becomes the wave,
Light has no rest mass, yet it bends the universe. It moves effortlessly through the void, crossing billions of kilometers without tiring, never slowing, never aging. It is both the messenger and the message, the means by which the cosmos reveals itself. But if gravity is born from energy, and if light carries energy, then light must also possess gravity. The question is not whether light can bend, but how deeply it can bend the fabric it travels upon. In the equations of general relativity, all energy contributes to curvature. Matter, radiation, and even pressure have their say in shaping space-time. A single photon has momentum, it can collide, it can push on matter, and therefore it has a gravitational field, however faint. In ordinary life, this is imperceptible, but in the immense scales of the universe, where light flows in torrents rather than beams, its gravity begins to speak. Imagine a region of space filled with radiation so dense that photons jostle and scatter like atoms in a gas. This is not an idle fantasy. It is the state the universe once occupied. In its earliest moments, light and matter were inseparable, locked in constant exchange. The cosmos was opaque, its glow so intense that photons could not travel freely. In that radiant ocean, gravity and light were not separate forces, but two aspects of one reality. The energy of the photons curved space-time, and that curvature guided the flow of the radiation. Only as the universe cooled did they part ways, allowing light to roam and space-time to smooth. Even now, that partnership endures in subtle ways. The light from stars, though faint when measured against their mass, contributes to their gravity. A luminous star is slightly heavier in its total curvature than a dark one of equal matter. The difference is minuscule, yet real. Across a galaxy filled with countless stars, the combined energy of starlight adds to the shape of the spiral arms, helping to sculpt the dance of gas and dust. The mathematics behind this is as elegant as it is demanding. The stress-energy tensor includes not only mass density, but also radiation density and pressure. Light's pressure, though weak, acts in every direction at once, curving space-time symmetrically. When immense amounts of light gather, their self-gravity becomes measurable. In theory, a beam of light with enough intensity could focus its own path through curvature alone, bending like a river folding into itself. There is a fascinating consequence of this. Two parallel beams of light moving in the same direction do not pull on each other. Their fields align perfectly, moving together at the same speed. But two beams moving toward each other attract. Each sees the other's energy as a source of curvature, and the space-time between them warps, pulling the beam slightly inward. This is the faintest whisper of light attracting light, a purely relativistic effect, too small to detect on human scales, but encoded in the structure of reality. Astronomers find indirect hints of this interplay in the vast brightness of quasars, those ancient beacons powered by black holes. Around their centers, light becomes so concentrated that it pushes matter outward, even as gravity draws it in. The equilibrium between radiation pressure and gravitational pull defines the boundary of what a luminous object can be before it tears itself apart. This limit, known as the Eddington luminosity, arises because light, in its own way, has weight. Too much radiation, and even gravity cannot hold it. The curvature caused by light is most easily seen not in its own field, but in its response to others. When photons pass through regions of extreme gravity, their paths bend, their frequencies stretch, and their energy shifts. We see this in gravitational lensing, where the light from distant galaxies arcs around massive clusters, forming multiple images of the same object. The lens not only magnifies but delays, forcing photons to travel along longer, curved routes through space-time. In those arcs and rings, we glimpse how tightly light and gravity are intertwined. If one could look closer, at the level of the equations themselves, one would see no boundary between mass and radiation, only gradients of energy and momentum. A photon, an electron,
a planet. They are all contributors to the same curvature. What changes is only the intensity of their effect. Light's contribution is small because each photon's energy is small, but in the aggregate, across the trillions of photons filling the cosmos, the effect becomes significant. The cosmic microwave background, the faint afterglow of creation, still carries about 5% of the universe's total energy. Its gravity is woven into the expansion itself, the rate at which the universe grows, the way galaxies drift apart, the subtle clumping of matter. All of these reflect the influence of ancient light still stretching through time. Even the faintest photon adds to space-time's shape, and that shape governs the path of every other photon that follows. There is a poetic symmetry in this. Light, which allows us to see the universe, also helps to build the very structure we see. It is the architect and the observer, the painter and the paint. In this sense, light does not simply illuminate geometry, it creates it. Yet, there is a limit to how much light can curve space-time before it becomes trapped by its own gravity. If enough radiation were confined in a small region, its energy density would be so high that it would collapse, forming a black hole of pure light. This is not hypothetical. It is a prediction of Einstein's equations. Such an object would be indistinguishable from a black hole made of matter. Its gravity would not care what the source energy once was. Whether born from dust or from light, the curvature is the same. This thought leads to something astonishing. If light can create gravity, and gravity can trap light, then the two are locked in an eternal feedback. The more light bends space-time, the more that curvature redirects the light. The result can be self-sustaining geometries, rings, orbits, and spheres of radiation balanced at the edge of collapse. Around black holes, we see the residue of this relationship. The photon sphere is where light's motion and gravity's pull find momentary harmony. But in principle, even a universe made entirely of radiation could hold its own structure through self-gravity. We live in the shadow of this truth. Every photon that leaves a star contributes to the grand dialogue between light and space-time. Each ray, each reflection, each glimmer participates in the shaping of the cosmos. The night sky, filled with light from uncountable sources, is also filled with the faintest whisper of gravity born from that light. When we say that light travels at the ultimate speed, we usually mean that it moves as fast as information can move. But in another sense, light defines that limit because it must carry the geometry it creates. It cannot travel faster than the curvature it produces, because that curvature is the stage on which it moves. Gravity and light are not rivals racing through space. They are two harmonics of the same vibration. And so the answer to the question is yes, light does have gravity. Its energy, its pressure, and its motion all shape space-time. The effect is small, but it connects the behavior of the smallest photon to the evolution of the entire universe. Light is the universe in motion, gravity is the universe in shape, and together they compose the single fabric of reality. To understand what happens when this balance reaches its limit, we must look to the place where light bends not just in response to gravity, but to itself, the photon sphere. There, gravity and light are no longer partners. They are one continuous motion. In that orbit, time nearly halts, and space-time curves so sharply that geometry begins to loop back on itself. At the photon sphere, we see what happens when light's own gravity completes the circle, binding energy to curvature in perfect equilibrium. Beyond it lies the edge of light's dominion, where gravity deepens until even the fastest thing in the universe cannot escape. That is where we go next, to witness gravity and light in their final dance at the boundary of the possible. There is a place where light no longer travels in straight lines. It circles endlessly, neither escaping nor falling, forever chasing its own reflection around the curve of space-time. This region, the photon sphere, is the edge where gravity and light balance with perfect tension. It exists just outside the event horizon of a black hole, where the pull of gravity
has become so strong that light's path bends back upon itself. Here, energy and geometry become the same thing. Imagine standing near that place, watching a beam of light orbit the darkness. The beam does not fade or stop. It moves at the same, unchanging speed, 299,792 kilometers per second. But the path it follows has no end. The curvature of space-time around the black hole is so precise that light can circle indefinitely, bound by its own motion. From a distance, it is as if gravity and light are locked in an endless race at the same speed, neither overtaking the other, neither free. The photon sphere sits at a distance of 1.5 times the Schwarzschild radius of a non-rotating black hole. That number may sound mathematical, but it represents something deeply physical. At that radius, the inward bend of space-time is exactly steep enough that a photon's natural straight line becomes a circle. The black hole does not pull on the photon as if by a force. Instead, it reshapes the very geometry that the photon follows. What looks like orbit is simply light obeying the rule of the shortest possible path in a curved universe. If you could hover just outside this sphere, the universe around you would appear strange and folded. Light from stars behind you would curve around the black hole, returning to your eyes from the front. You could see the back of your own head. Every direction would hold echoes and distortions of the same sky. The boundary between forward and backward, up and down, would lose meaning. You would be standing in a hall of mirrors made of space-time. In that place, time itself slows. To an outside observer, the orbiting photons seem frozen, locked in eternal loops. Yet for the light itself, no time passes at all. For a photon, time does not flow. It experiences its entire journey as a single moment, a continuous existence without before or after. The photon sphere is the visible manifestation of that paradox: motion without passage, change without time. Here we can see, with almost painful clarity, what Einstein's vision of the universe means. Gravity is not a force pulling objects together. It is the warping of the stage on which they move. In this warped stage, the path of light becomes circular, not because it is being dragged, but because the geometry leaves it no other choice. The shortest route, the path of least action, now loops forever. If we could send two beams of light in opposite directions around the photon sphere, they would circle endlessly, crossing each other again and again, weaving a perfect ring of brightness. That ring is what telescopes now see when they image the shadow of a black hole, the thin halo surrounding darkness. It is not the black hole itself that glows, but light from behind it, captured by its gravity, orbiting for a moment before escaping toward us. The glow is the evidence of space-time's curvature made visible. To understand the physics behind this, we look again at the balance of energy and geometry. The gravitational potential at the photon sphere is such that any slight deviation inward or outward destroys the orbit. A photon nudged outward will spiral away into the cosmos. One nudged inward will plunge into the horizon and vanish. The photon sphere is not a stable resting place, but a knife edge of equilibrium, a region defined by perfection so fragile that nothing can remain there for long. And yet, in that fleeting balance, we see the union of the universe's two great constants, the speed of light and the curvature of space-time. The photon sphere is their meeting point, the moment when energy moving at the ultimate speed bends itself through the geometry it creates. The photon does not slow, gravity does not accelerate, and still they circle together. This phenomenon has been confirmed not only through theory, but through observation. The Event Horizon Telescope's image of the black hole at the center of galaxy M87 shows a glowing ring of light, bright on one side, dim on the other. That asymmetry arises from motion. Light moving toward us appears brighter, while light moving away is dimmed by redshift. Yet all of it traces the same invisible orbit around the black hole's shadow. The photon sphere
shining across unimaginable distance. This place, halfway between freedom and capture, challenges our notions of direction and flow. The photon sphere is not merely a circle in space, it is a turning point in the relationship between light and gravity. Outside it, light can still escape. Inside it, all paths curve inward. At the sphere itself, light and gravity exist in perfect equilibrium, locked at the same speed, defining one another. If we imagine the universe as a grand conversation between motion and geometry, the photon sphere is where that conversation becomes a single voice. The message and the medium merge. Energy no longer merely travels through space-time, it becomes space-time's motion. The curvature and the light are one expression of the same reality. For all its beauty, the photon sphere is only the prelude to something even stranger. Beyond it lies the event horizon, where not only light, but time itself becomes captive. At that threshold, gravity does not move faster than light. It ceases to move at all, for there is no longer any outward direction to travel. Space-time curves so completely that every line of motion leads inward, and causality itself turns toward the singularity. The photon sphere shows us the last moment when the universe's two most fundamental properties, speed and curvature, can coexist without collapse. Beyond it, gravity bends the fabric of reality until light and time share the same fate. The equations do not break, they reveal their full depth. The speed of light remains constant, but the meaning of distance and direction dissolves. This is not a failure of nature's laws, but their fulfillment. The photon sphere, fragile and perfect, stands as a boundary not of matter, but of meaning. It marks the transition between the world we can observe and the region where observation becomes impossible. It is the limit of knowledge made visible. In this way, the photon sphere is both a scientific fact and a philosophical mirror. It tells us that the universe's greatest mysteries are not hidden beyond reach, but written into the very geometry that allows us to see. Light does not simply reveal the cosmos, it reveals itself, bending into circles to show us that knowledge has edges, and that beyond those edges lies the infinite depth of the unknown. There is a line in the universe beyond which light can never return. It is not a wall, not a barrier of matter, but a boundary in geometry. This is the event horizon, the edge of light. At this threshold, the escape velocity equals the speed of light, and every possible path through space-time curves inward. Nothing physical holds light captive. Instead, the shape of reality itself changes until outward and inward become the same direction. Approaching this boundary is like moving through a vast ocean of slowing time. From a distance, you would see the clock of a falling object tick slower and slower as it neared the horizon. The light it sends would stretch into red, its signals lengthening until they fade completely. To you, the object never quite crosses the boundary. It appears to freeze, hovering forever just above the edge. But from the object's own perspective, nothing unusual happens. It continues inward, crossing the horizon in a single smooth motion. This is the paradox of gravity at the speed of light. Both observers are correct, each within their own geometry of time. At the event horizon, light no longer has an escape route. The curvature of space-time is so severe that every geodesic, every natural path a photon could follow, bends back inward. The photon still moves at its usual speed, 299,792 kilometers per second, but the surface it moves upon has folded so deeply that all motion leads to the center. The speed of light remains constant, but the meaning of distance has changed. To understand this, one must stop imagining gravity as a force pulling things down. Gravity does not act through space, it creates space. In a strong gravitational field, space-time itself flows inward, like a river falling toward a whirlpool. Light rides the current, always moving locally at the same speed, yet globally drawn toward the abyss. The event horizon is the point where that inward flow equals the speed of light. Beyond it, even a beam of light moving outward cannot overcome the inward motion of space-time.
It is as though the river falls faster than the fastest swimmer can swim. The beauty of this realization is that nothing breaks. Physics does not fail beyond the horizon. The speed of light remains sacred, the equations still hold, but the geometry has twisted into a form where all directions lead toward the singularity. Space and time exchange roles. What we call time becomes the direction of inevitability, the one path every particle must follow. To move forward in time is to fall inward through space. To the outside universe, the event horizon is a perfect mirror of mystery. No light escapes, no information returns, yet it is not a surface that absorbs in the way matter does. It is a boundary in causality. The events beyond it still unfold, but they are sealed from the rest of the cosmos by space-time itself. Gravity here is not faster than light. It is geometry beyond reach. From this perspective, the event horizon is less a place and more a condition of reality. It marks where the inward flow of space-time outpaces every outward possibility. And this same principle holds for all black holes, large or small. Whether formed from a collapsing star or existing at the heart of a galaxy, the horizon is always the boundary where light's own speed becomes the measure of confinement. If we could hover just outside this edge, our instruments would detect strange distortions. The light from the universe behind us would bend and stretch, wrapping into halos. The glow of the accretion disk, matter spiraling inward at nearly light speed, would shine in furious arcs, its energy converted from motion into radiation as friction and gravity tear it apart. All the while, time would run slower near the horizon than it does farther away. A second there could equal hours, even years, to a distant observer. This is the ultimate test of Einstein's vision. The same curvature that slows time also traps light. Space and time are not separate. They are threads of one fabric, stretching and warping under the weight of energy. The event horizon is the deepest fold that fabric can take without tearing. Beyond it, the equations still describe motion, but that motion leads to a singular destiny. The most astonishing truth is that gravity never breaks the light speed limit, even here. The flow of space-time at the horizon moves at light speed relative to the outside universe, but not faster. No signal, no vibration, no gravitational wave can escape once inside. The gravitational influence we feel from a black hole comes entirely from the region outside the horizon, from the curvature frozen in place when the black hole first formed. The field itself does not emerge from within. It is the geometry left behind, perfectly static, propagating its influence outward at light speed. Seen this way, a black hole is not a hole at all, but a region of space-time sealed by its own perfection. It is the final expression of gravity's obedience to the cosmic limit. The curvature is complete, the flow absolute. Light circles, time slows, and all paths converge inward. Yet the equations remain smooth. The universe bends but does not break. This is why the horizon is so compelling, not for what lies within, but for what it tells us about the nature of reality itself. It is the line where light speed defines, not just motion, but existence. Everything that happens beyond the horizon is still happening in accordance with that same law, but hidden behind the veil of geometry. The black hole does not defy the universe's rules. It embodies them so completely that the rest of the cosmos can only see the boundary of its perfection. To an outside observer, gravity at the edge of light seems eternal, unmoving, almost infinite. To the universe itself, it is simply the point where motion and geometry become indistinguishable. The event horizon does not mark the end of physics. It marks the moment when physics becomes pure geometry. And as light fades into that darkness, the last visible remnant is the photon sphere, glowing faintly with the reflection of the universe it no longer escapes. Beyond that halo, gravity does not race ahead of light. It curves the very space that defines the race. Time and distance dissolve,
and the fabric of reality folds into the shape of its own speed limit. But what happens to gravity as it moves through such a curved environment? How do gravitational waves, those ripples of space-time itself, behave when trapped near such extremes? Do they slow, stretch, or vanish? To answer that, we must follow gravity's motion within the storm to the propagation of curvature itself under the most violent conditions the universe can create. When gravity moves, it does not rush through space like wind or current. It ripples through the very geometry of the universe. Those ripples are gravitational waves, the purest form of motion that space-time can create. They carry no substance, no particles, and no light. They are space-time itself in motion, trembling as energy shifts and matter changes its arrangement. When massive objects move violently, two black holes colliding, a neutron star collapsing, a galaxy quivering with merger, the geometry of the cosmos rings like a vast, invisible drum. These waves travel outward at the speed of light. They do not move faster, because they are not signals within space. They are the movement of space itself. When one passes through a region of the universe, distances stretch and contract by the smallest imaginable fraction. Atoms tremble, rulers lengthen and shrink, and clocks tick at slightly different rates. Then the wave is gone, leaving no trace but the memory of motion itself. In the calm of ordinary space, these ripples are faint. The universe is remarkably rigid. To create a measurable gravitational wave, one must move entire stars at speeds near that of light. When black holes merge, their combined energy briefly outshines all the stars in the visible universe, not in light but in pure curvature. That energy spreads outward, crossing billions of light years, weakening with distance but never slowing. Yet when these waves pass near regions of intense gravity, around black holes, near neutron stars, or through the dense web of the early cosmos, their paths bend and stretch just like light. They do not slow down, but their wavelengths change. The curvature of space-time alters the distance they must travel. The waves redshift and fade, their frequencies lowering as the geometry expands or deepens. Gravity affects itself through its own curvature. If we could watch space-time from outside, we would see those waves shimmer and distort as they pass through gravity wells, twisting and stretching as they move. Their form would resemble ripples passing over deep water, steady but refracted by the depths below. Where space-time curves sharply, the waves would scatter and merge, forming complex patterns of interference. Yet through it all, their speed remains constant, for there is no faster way for the universe to communicate change. The equations that govern these waves are intricate. They tell us that space-time has stiffness, a kind of elastic resistance to distortion. But unlike an ordinary medium, space-time's stiffness is defined by the very geometry it describes. The stronger the gravity, the more the waves are redshifted. Not because they lose speed, but because time itself stretches. Near a black hole, gravitational waves fall into the same rhythm as light, circling and lingering before finally escaping to the wider universe. In computer simulations, when two black holes merge, the resulting space-time oscillates like a struck bell. The pattern of those oscillations, called the ringdown, depends entirely on the mass and spin of the final black hole. Each frequency encodes information about the geometry itself. The waves we detect on Earth are not merely echoes of distant collisions. They are messages written in the vibrations of space-time, carrying the fingerprints of the universe's most extreme structures. When gravitational waves travel through curved regions, their amplitude weakens more slowly than that of light. This is because they are not absorbed or scattered by matter in the same way. They pass unhindered through stars, planets, and entire galaxies. Even if they encounter other gravitational fields, they are altered only by the geometry, not by the presence of material obstacles. This makes them the perfect messengers for observing the universe's most hidden events. But there is a deeper meaning to this behavior. It shows that gravity never stops communicating. Even in the most violent, chaotic corners of creation, space-time transmits its story outward at the same universal rate. Nothing outruns it, and nothing lags behind. Gravity is both the actor and the narrator, shaping and reporting the unfolding of the cosmos simultaneously. Near the event horizon of a black hole, gravitational waves behave differently. They are stretched and slowed from our perspective, drawn out endlessly by the time dilation of extreme curvature. To a distant observer, they seem to freeze, their energy redshifted into silence. But to the geometry itself, the waves continue inward at light speed, merging seamlessly with the structure of the horizon. There is no barrier, only the change in what time and distance mean. This duality, waves that move through time and yet define time, is the essence of gravity at light speed. The ripples of space-time can never move faster than light because they are not separate from it. Both are bound to the same causal structure. Both define what can influence what. The cosmic limit is not a restriction. It is the order that gives the universe coherence. Every detection of gravitational waves confirms this truth. When we measure the tremors from a distant merger, we are feeling the rhythm of the cosmos as it updates itself. The waves arrive in perfect synchrony with light, sometimes delayed only by the path they must take through curvature. Their agreement with the predictions of relativity is astonishing. Within 1 part in 10 to the power of 15, they move at exactly the same speed as photons. There is poetry in this. The same speed that carries light through the cosmos also carries the vibrations of space-time. The same rhythm that defines brightness defines gravity's voice. The universe does not allow discord between them. They are harmonics of the same symphony, two expressions of one fundamental truth, that causality and geometry are inseparable. In extreme environments, such as during the formation of a black hole or the inflation of the early universe, these waves become more than ripples. They become architects. Their interference shapes how matter gathers, how galaxies form, and how the large-scale structure of the universe unfolds. They carry information not only about the past, but about the boundaries of possibility. As they move outward, they stretch with the expansion of space itself. The universe's own growth redshifts them, lowering their energy while preserving their speed. The oldest gravitational waves, those born in the first moments after creation, still travel among us. Their wavelengths stretch to sizes larger than galaxies. They are the background hum of existence, the first heartbeat of time continuing forever. To listen to those waves is to hear the universe itself speaking in its native tongue. It is not a voice of sound or light, but of curvature. It tells of stars collapsing, of horizons forming, of energy flowing through geometry. It reminds us that everything that happens, from the fall of a stone to the merging of galaxies, reverberates through space-time. Gravity does not stop. It cannot. Its waves propagate eternally, defining the fabric of causality. They do not need a medium, for they are the medium. They do not travel through space. They are space in motion. When we understand this, the universe becomes something greater than a stage filled with forces. It becomes a living geometry, an endless, self-communicating web, where light and gravity are the same pulse, seen from different sides of reality. But what happens when motion itself reaches that pulse's limit? What does gravity become when energy moves at light speed? When mass compresses so completely that space-time reacts instantaneously within its own constraint? The next step takes us to that frontier, the ultimate limit where gravity becomes a shockwave and reality itself flattens into motion. As motion nears the speed of light, the universe itself begins to shudder. Distances contract, time stretches, and what once seemed infinite becomes narrow and sharp. Every increase in speed demands an even greater surge of energy, until that energy begins to bend the very geometry through which it moves. The boundary between motion and gravity starts to dissolve. This is the ultimate limit, the frontier where space-time and energy face each other with equal strength. According to Einstein's equations,
Energy and mass are two expressions of the same quantity. A particle's energy increases as its speed rises, and with that energy comes greater curvature. In the quiet calm of low velocities, this curvature is so small that it can be ignored. But as motion climbs toward light speed, the energy grows without bound. Each attempt to accelerate further demands more energy than the last, until, near the limit, the entire universe would need to lend its power to move the particle a fraction faster. The mathematics are clear. As speed approaches light, energy approaches infinity. And infinite energy means infinite curvature. What happens to gravity under those conditions? How does space-time respond when energy becomes so concentrated that its own geometry can no longer remain smooth? The answer lies in one of the most extraordinary solutions to Einstein's field equations, the Eichelberg-Sechsel ultraboost. It describes the gravitational field of an object accelerated to the speed of light. In that limit, the usual spherical field of gravity collapses into a razor-thin plane, infinitely compressed in the direction of motion. The space-time curvature no longer spreads evenly around the moving mass. Instead, it is flattened and intensified, forming a gravitational shockwave that races forward at the same speed as light itself. The object no longer drags its gravity behind it. It carries it along as a sharp, instantaneous distortion of geometry. This is gravity at light speed, a pulse of space-time, a perfect synchronization of energy and geometry. It does not move faster than light, but it expresses motion at the very edge of possibility. The field is not extended through space. It is confined to a single moving plane, an infinitesimal wavefront that displaces space-time as it passes. Behind it, space-time returns to calm. If we could visualize this, we would see space-time as a fluid ocean and the object as a pebble hurled through it at infinite energy. Instead of creating ripples, it creates a single, flat wave that travels with it forever. There is no wake, no aftermath, only an instantaneous compression followed by stillness. The concept might seem abstract, but it has profound physical meaning. When two such waves collide, when two ultra-relativistic particles meet head-on at near light speed, their combined curvature can briefly become so intense that space-time collapses inward. A horizon forms, microscopic and fleeting. For a moment shorter than the blink of an atom's vibration, a black hole is born and vanishes. These theoretical events could occur wherever particles collide with enough energy, such as in the earliest instance of the universe, or in the collisions of ultra-high-energy cosmic rays striking atoms in Earth's atmosphere. The mathematics behind these possibilities reveal a strange truth. The closer one gets to light speed, the more gravity becomes directional. It no longer radiates equally in all directions. Instead, it focuses forward, like the beam of a cosmic flashlight. The curvature compresses into the direction of motion. This is a manifestation of Lorentz contraction, the geometric shrinking of space along the axis of velocity. From the viewpoint of space-time, the object's presence becomes thinner and denser, its gravitational field sharper and more violent. This flattening means that gravity itself becomes a wave, an instantaneous distortion moving with its source. At this limit, energy and geometry cease to be distinct. Motion becomes curvature, curvature becomes motion, and space-time transforms into the thing being moved. There is no distinction between the traveler and the road. In the world of high-energy physics, this idea is not fantasy, but a necessary consequence of relativity. Every accelerator, every beam of particles, every cosmic ray tests this principle. When protons are smashed together at near light speed, their fields compress in precisely this way. Though we cannot see the gravitational distortion directly, it is far too weak to measure. The equations show it must exist. Were the energies higher by many orders of magnitude, enough to approach the Planck scale, those distortions could curve space-time violently enough to form transient micro-black holes. The Planck scale marks the point where gravity and quantum mechanics must finally meet. At that scale, where distances are as small as 10 to the power of -35 meters and energies as great as 10 to the power of 19 giga-electron-volts, our understanding of space-time ceases to be smooth. Geometry itself may become quantized, breaking into discrete packets of curvature. At that frontier, the gravitational shock waves of light-speed energy could reveal the building blocks of space-time itself. If we could see a single Planck scale collision, it might look like this. Two pulses of geometry rushing toward each other at light speed, colliding and merging into a knot of curvature, then exploding outward as gravitational waves. For an instant, shorter than any measurable time, the universe would fold in on itself and rebound. Each such event would be a miniature version of creation, a burst of energy where geometry becomes fluid. This is not only theory. Observations of the most energetic cosmic rays, particles striking Earth's atmosphere with energies 1,000,000 times greater than those in our most powerful colliders, hint at this frontier. They move so close to light speed that time for them nearly stops. Their gravitational fields are almost flattened, their energy densities almost unimaginable. Yet even they cannot reach the ultimate limit. The universe itself prevents it, because to reach it would be to turn into space-time's own motion. The deeper we explore this, the more we realize that light speed is not merely a cap on velocity. It is the point at which the concepts of speed and distance dissolve. For a photon, there is no passage of time, no sense of journey. It does not experience space as we do. Its entire existence, from emission to absorption, is a single timeless event. For gravity at light speed, the same is true. The gravitational shockwave is not traveling through time. It is the geometry of an event that exists all at once. In this sense, motion at light speed is not motion at all. It is the universe expressing an identity. A photon is not something that moves. It is the shape of space-time that connects two points causally. A gravitational wave is not something that travels. It is the changing of geometry itself. When mass approaches light speed, it begins to behave like these entities, not as an object in motion, but as a transformation of space-time's form. The ultraboost solution shows that at this limit, space-time flattens in one direction and expands in another. The result is not destruction, but a change in how curvature communicates. Gravity becomes instantaneous only within its own light cone, never beyond it. The universe's causality remains perfect. No signal or wave can leap ahead of light, because the fabric of cause and effect is the same thing that defines light speed itself. There is beauty in this discipline. The universe never allows contradiction. Even when energy bends space-time to the brink of collapse, the rules remain exact. Nothing outruns light because light is the universe's own rhythm, the heartbeat of geometry. Every field, every wave, every form of motion is constrained by it, synchronized to it, dependent on it. The moment an object moves at light speed, it ceases to be matter. Its energy becomes pure motion, pure curvature, pure space-time. In that transition lies the bridge between physics and philosophy. The universe guards its limit not through force, but through transformation. It does not forbid light speed, it turns everything that reaches it into something new. Imagine then what it means for gravity to reach this point. A gravitational shockwave is space-time itself moving at its own limit, a self-communication of the universe about its own state. It is the cosmos speaking in the only language it knows, the geometry of causality. Each wave is a message about change, traveling through the structure that defines the meaning of travel. At the most extreme energies imaginable, this principle could define the shape of the early universe. During the first trillionth of a second after creation, space-time was flooded with waves and pulses moving at light speed. There were no stars, no atoms, no distinction between matter and energy. There was only curvature in motion, a cosmic sea of geometry vibrating with unimaginable intensity. From that chaos came order,
As the universe expanded and cooled, energy slowed, matter formed, and gravity took on the gentle forms we now see. But beneath that calm lies the memory of that initial storm, gravity at light speed, woven into the universe's foundation. Modern experiments search for echoes of that storm. The faint hum of primordial gravitational waves stretched across the cosmos by cosmic inflation still fills space today. They are almost impossible to detect, their wavelengths longer than galaxies, their energy dispersed across time itself. Yet if we could hear them, we would be listening to the voice of gravity at the speed of light, the first sound the universe ever made. The significance of all this is profound. It tells us that the ultimate limit is not merely physical, but existential. Light speed is not a number to be surpassed. It is the definition of what can exist. To move faster would be to step outside space-time, to leave the realm of cause and effect, to become meaningless within the universe's language. That is why nothing can cross that boundary, because beyond it, there is no framework for meaning. The cosmic speed limit is not a prison. It is the architecture of reality itself. It ensures that every motion, every event, every moment is connected in an unbroken chain of causality. It gives the universe structure, coherence, and beauty. Without it, the cosmos would be chaos, a place without order, without history, without time. And so, as we reach this final understanding of motion and gravity, we find ourselves not staring at a barrier, but at a mirror. Light speed reflects the nature of being. It shows us that the universe is both finite and infinite, bounded by laws, yet open to endless depth. Gravity at light speed is the universe's way of showing us its own perfection, the point where energy and geometry merge into one continuous identity. Nothing outruns it. Nothing surpasses it. Every particle, every photon, every ripple of space-time dances to its rhythm. The ultimate limit is not an obstacle to exploration. It is the very reason exploration is possible. It holds the universe together and gives time its direction. It defines what can be known, what can be changed, and what can exist. Gravity at light speed is not a contradiction. It is the purest expression of the universe's unity. Motion becomes curvature, energy becomes form, and space-time becomes its own messenger. It is the point where reality reaches its perfect tempo. At that frontier, where mass, motion, and geometry blur into one, the cosmos reveals its secret. The speed of light is not just a speed. It is the speed of causality, the speed of reality, the speed at which existence itself unfolds. There is a law woven through every atom, every galaxy, every horizon. It is not written in language or light, but in the rhythm of space-time itself. That law is the constancy of light speed, 299,792 kilometers per second. The number is not arbitrary. It is the defining tempo of the cosmos, the pulse that keeps time for reality. Every particle, every vibration, every field moves in step with it. It is not merely how fast light travels, it is how fast existence unfolds. In Einstein's revelation, light speed became something far greater than a velocity. It became the structure that ties cause to effect, motion to meaning. It is the universal agreement of reality, the rate at which information can flow, the cadence by which time itself measures its passage. To move faster would be to move outside of causality, beyond the reach of time, into a realm where the sequence of events dissolves into incoherence. The universe forbids this, not as a matter of enforcement, but of definition. Nothing can exceed the speed of light, because light speed defines what it means for one thing to influence another. We often imagine the cosmic limit as an external constraint, a wall placed upon nature. But the truth is subtler. Light speed is not a prison. It is the geometry of freedom. It allows the universe to maintain coherence across unthinkable distances. When a star flares in one corner of the cosmos, the ripple of that event travels outward at light speed.
ensuring that every distant world learns of it in perfect rhythm. No information jumps ahead, none lags behind. The result is a universe that speaks to itself with flawless timing, a vast and intricate conversation held across billions of light years. Gravity joins in that conversation, whispering in the same tongue. It propagates through space-time not as a force, but as a change in geometry. When a star moves or collapses, the curvature of space-time adjusts, and that adjustment spreads outward at the same speed as light. The universe updates itself in perfect synchrony. Even black holes, those deepest wells of gravity, respect this tempo. Their influence does not reach outward instantaneously, but ripples through space at light speed, maintaining causality even at the edge of time. This unity between light and gravity is not coincidence. It is the natural outcome of Einstein's field equations. Both are modes of the same fabric. Light follows the curvature of space-time, and gravity is the curvature itself. One traces the geometry, the other defines it. They are two aspects of the same cosmic symphony, light as melody, gravity as harmony, together composing the structure of reality. In this vision, the universe is not made of things moving through space, it is made of motion itself. Space-time is not a stage on which events occur, it is the event. Matter, light, and gravity are patterns within that event, expressions of the same underlying geometry. When we measure distance or time, we are really measuring how the geometry has stretched and twisted in response to energy. Every tick of a clock, every step across a room, is a small act of curvature playing out according to the same unchanging rhythm. At the edge of this understanding lies a truth that borders on the philosophical. Light speed is not simply the limit of how fast something can travel, it is the limit of what can exist. To move faster would require traveling outside of space-time, stepping beyond causality into a domain where before and after lose meaning. Such motion cannot occur because it would have no place to occur in. Beyond the speed of light, there is no geometry left to describe the journey. Even the concept of time dissolves at this boundary. For an object with mass, time slows as it accelerates, its internal processes stretching out. At light speed, time ceases entirely. For a photon, the entire journey from one end of the universe to another is instantaneous. It does not experience distance or duration. Its entire existence is one continuous event, emission and absorption as a single act of being. Light does not travel through space-time. It is space-time in motion. Gravity, too, follows this rule. When we speak of gravitational waves moving at light speed, we are describing space-time vibrating at its own natural frequency. These waves do not move through a medium. They are the medium. They are the universe changing itself. At the speed of light, gravity and light are indistinguishable in their obedience to causality. Both are expressions of the same underlying unity. In the most extreme regions, near black holes, neutron stars, and the remnants of stellar collapse, this unity becomes visible. Light bends around mass, following the curved lines of space-time. Time slows in deep gravity wells, distances distort, and the geometry itself becomes dynamic. Yet through all this, the speed of light remains constant. Even where gravity twists the path of light into a loop, as in the photon sphere, the local speed never changes. The constancy of light speed holds not because of what light is, but because of what space-time is. This constancy has profound implications for the shape and destiny of the universe. It defines the expansion of space, the formation of galaxies, and the evolution of stars. It limits the range of possible futures and ties every cause to its eventual effect. The cosmic web, stretching across billions of light years, exists in delicate harmony with this law. If the speed of light were even slightly different, stars might never form, matter might not cohere, and time itself might unfold in chaos. The universe's elegance arises from this balance. From the human perspective, this truth is almost paradoxical. We are creatures bound to slowness, living in a world where even sound seems swift.
Yet everything we see, every color, every sunrise, every glimmer of starlight, is a message traveling at the ultimate speed, bound by the same rule that governs black holes and galaxies. Each photon that strikes our eyes has crossed a cosmic distance with perfect fidelity, obeying a law that has held since the birth of time. If light defines the universe's limit, gravity defines its shape. Light tells us how fast information can move. Gravity tells us how that information curves the universe as it goes. The two together form the architecture of existence. Without light, the universe would be static and silent. Without gravity, it would be structureless chaos. It is their interplay, the ceaseless dialogue between motion and form, that gives the cosmos its depth, its beauty, and its story. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. That comprehension arises because the universe behaves consistently. The speed of light ensures that cause always precedes effect, that geometry remains continuous, that reality does not tear. It is the foundation of all understanding, the bedrock beneath every law of physics. When we look at the stars, we are not seeing them as they are, but as they were, their light traveling across time to reach us. The delay is not a flaw. It is the universe's way of preserving order. Every photon that arrives carries the memory of where and when it came from. Every gravitational wave that sweeps through space is a record of motion and mass encoded in the curvature of space-time. Together they form a cosmic archive, an unbroken record of everything that has ever happened. Perhaps this is the deepest meaning of the cosmic speed limit. It ensures that the universe remembers itself. Without it, the chain of causality would break and memory would dissolve. The laws of physics would lose coherence. The speed of light is the universe's memory made law, the rate at which reality updates its own story. As our understanding deepens, we begin to see that this speed limit is not a boundary to be overcome, but a bridge between understanding and wonder. It is a constant reminder that even in a universe governed by equations, there is harmony and grace. Light speed is the measure of that harmony, the pulse that keeps existence in time. And so, the universe continues its rhythm. Gravity propagates at light speed, light bends to gravity's will, and time flows in accordance with both. Matter and energy, space and time, dance together in perfect synchrony. Each is bound to the other, each defines the other. Nothing outruns this relationship because nothing exists outside of it. In the end, we discover that the speed of light is not only a physical constant, it is the essence of being. It is how the universe knows itself. Every sunrise, every orbit, every heartbeat occurs within its measure. It is the cosmic metronome, the steady beat that drives the symphony of creation. At the speed of light, time slows, matter blurs, and gravity becomes geometry itself. Beyond that speed, there is no beyond. There is only space-time, curving forever at the speed of reality, weaving light and gravity into one endless act of existence.